Bon, je m'appelle Raphaël. Je voulais vous présenter Michael Hrusak aujourd'hui, qui nous vient à partir du Mexique. Et vous permettez deux conseils de ma part. On voit toutes sortes de choses néfastes dans les médias au sujet du Mexique. Alors, j'aimerais vous signaler deux choses, deux suggestions. Premièrement, si vous avez la chance de visiter la ville de Mexico, allez voir le musée d'archéologie. C'est fantastique, ça va changer, ça va vous changer. Ça va vous changer. C'est comme le Louvre. Après une journée, vous allez sortir du musée une personne différente. Deuxièmement, vous pouvez vous approcher. Il y a une école de topologie au Mexique qui comprend toutes sortes de personnes intéressantes, y compris Michael. Et je vous conseille de vous mettre en contact avec eux. So I will switch to English. I'd like to present Michael Hrusak today. I just said in French, if you ever have the chance to go to Mexico, you'll see some stuff that you don't see on the news reports up here. And I suggest to you that you consider visiting the Museum of Archaeology in Mexico City. It is a wonder of the world, frankly. And secondly, get in touch with the topologists in Mexico. There's really now sort of a school in Mexico, all sorts of interesting people. One of them is a student of Archangelski, and another is our speaker today, Michael. Now, recently, I read an introduction to a book, and at the beginning of the introduction, there was a very, very brief introduction by Sigmund Freud, who said that he thought this book was of some value. Okay, short and sweet. So our speaker today, Michael, I know from personal experience, is an interesting person, and I think he's a very talented person. He works in set theory. So Michael, you're going to talk to us about set theory and topological algebra. Right?
I will, yeah. Well, thank you for the introduction, and thank you for having me. Thank you for the invitation. I think I've never spoken in Montreal before, so it's a great first for me. Yeah, I want to tell you something about, of course, the title is very pompous, the set theory and topological algebra. I could be talking about anything. I usually do that because I want to give the titles before I really decide what I'm going to talk about, and it gives me more chances. So, so as I said, I'm a set theorist by training, and set theory likes to lay claim to being a foundational thing in mathematics. But of course, it has this rather annoying feature of independence, the Gödel's incompleteness theorem. So I think that it's our job as set theorists to look for the boundaries of this independence phenomena in all throughout mathematics, and that's part of what I'll be doing today. What do I mean by that? Well, you hear that somebody proved that some statement is consistent. So you go and look closer at that particular statement, and there are two possibilities. So either you can improve the proof to make it a ZFC result, or you can prove consistency of the negation and prove that the statement is independent, and that sort of would be the bad news. I will have examples of both today. And the other thing is just there are a set theorist toolbox, which includes many different things, and logicians toolbox and model theory toolbox. Set theory is sometimes confused with logic. So the other thing is just to show that some of these things from that toolbox can be of use to other areas of mathematics. And in particular, I'll be talking about topological algebra, which is mostly a shortcut for talking about topological groups. Now, I can see a lot of people here who I know have interest in particular topological groups, Polish groups, say, or simply infinite discrete groups, which are not much topological. So I will be, at least through most of my talk, I will be looking at more complicated groups. So they could be countable or uncountable, but usually the topologies are going to be more complicated than just metric. Having said that, the theme in topology is that often adding algebraic structure to topology improves on the behavior of properties. So for instance, in topology, metrization problems are rather important and complicated. And in topological groups, they become simple. So Hausdorff topological group or T1 topological group is metrizable if and only if it has a countable local basis at the identity. So that's just an example. And what I'll be concentrating on most of the talk, at least today, is on looking at the role convergent sequences play in the study of topological groups. And just to highlight how little we still know about that, even in the general topological context, I want to remind you of this open problem in topology. So it's still, and to me, it's mind-boggling that almost 100 years after the study of topology, we still don't know an answer to such a basic problem in topology. So if you have a compact topological space, all spaces are Hausdorff, does it either contain a smallest compactification? This is one of those problems that I talked about before. There are consistent counterexamples. So, for instance, diamond principles and several other models give counterexamples to this, but we don't know if there is a ZFC counterexample or if a positive answer is consistent.
But it doesn't say group.
It doesn't. That's why I didn't talk about group, because for groups, this is known. Every compact group does contain a convergent sequence, so you don't even need these two alternatives. You are always on the safe side of just having one. And so I will split my talk into 2 or 3 parts, depending on time. So definitely 2 parts. And in the first part, I will be talking about topological groups which have no convergence copies of convergent sequences at all, meaning every convergent sequence is eventually constant as a sequence. So it does not contain the space of a convergent sequence. And in the second part of the talk, I will be talking about groups which have many convergent sequences. So groups where actually the topology is determined by convergent sequences. So let's go to the first one. So I'm a set theorist, and I just can't help myself. So everywhere I should write n for the natural numbers, I write omega for the finite ordinals. And if I tried to be consistent with n, I would fail still, so I stopped. So this is just a disclaimer for everybody who's not happy with ordinals. So if you don't like ordinals, every time you see omega, think n. So things just countable set. And so the first sort of set theoretic tool I want to talk about is a very simple one. It's an ultra filter. So everybody knows that filter, what a filter is, I think, I hope. So filter is in a measure theoretic terms, these are measure 1 set by definition, okay? So if you have a measure 1 set, so everything is of measure 1, empty set is of measure 0. And if you have a measure 1 set, a bigger set is of measure 1, an intersection of 2 measure 1 sets is again of measure 1. So this is a filter, and we require that no finite set, all finite sets have measure 0. And if such a filter is maximal, that means it measures by 0 or 1 every set of integers. So every set of integers has either measure 1 or measure 0, then we call such a filter an ultra filter. Now, this is a set-theoretic object. You may ask me, give me an example. I cannot. And the reason why I cannot, that you have to invoke the axiom of choice to show the existence of these objects, but they are very useful throughout the mathematics nonetheless. I will be denoting ultrafilters by P and Q because of my topological upbringing, because I often think of them in terms of the checkstone compactifications where they become points. All right. And so what are we going to do with ultrafilters? First, we will take a look at compactness properties. So if you have a sequence and an ultrafilter, or a filter in general. So what does it mean that a sequence converges? In general, it just means that every neighborhood, so it's a sequence of n which converges to x, it just means that every neighborhood takes all but finitely many elements of the sequence. In the ultrafilter language, it just means every neighborhood takes measure one many points of the sequence measured by the ultrafilter. Okay, so that's what a P limit means. What's the advantage of taking ultrafilters? That every sequence, if it accumulates to a point x, the point x is a P limit for some ultrafilter P. Okay, and so let's take a look at some of these standard compactness-like properties. So everybody knows what a compact space is. Every open cover has a finite subcover. A P-compact space is a space where every sequence has a P limit for some fixed ultrafilter P. A countably compact, which is actually was the original definition of compactness in Fraissé's book, just requires that every countable open cover has a finite subcover, and equivalently, this means that every sequence has a P limit for some ultrafilter. So the difference between P compact and countably compact is just switching of ultrafilters. So P compact says there is a P such that for every sequence I have a P limit. Countably compact says for every sequence there is a P such that I have a P limit. Okay, and finally, pseudo-compactness is the property of compact spaces, or a property of spaces that every real valued function, its image in the reals is bounded. Okay. The properties get successively weaker as I defined it. So every compact space is P compact, every P compact space is countably compact, every countably compact space is pseudo-compact. If you have any questions at any time, please interrupt me. I forgot to say that at the beginning. And they behave differently when it comes to products. So I want to take a look at how they behave with products. So it's the famous Tikhonov's theorem says that any product of compact spaces is compact. And it's a trivial consequence of the definition that any product of P compact spaces is P compact. And as far as spaces go, this is where it stops, because it has long been known that products of countably compact spaces not only don't need to be countably compact, they don't need to be even pseudo-compact. And so it came as a surprise, but it's sort of a theme, as I said. Algebra improves things, that this Comfort-Ross theorem says that if you take arbitrary product of pseudo-compact groups, topological groups, then the product is again pseudo-compact. And it prompted with Comfort to ask the obvious question, what about countably compact? And that question has remained open since '66, well, up until, say, 1980, where it was given a partial solution. So Eric van Douwen was the first one to construct consistent counterexamples. So he constructed two countably compact groups whose product is not countably compact. And the way he did it was he first constructed a single group, countably compact, which had the property that it had no non-trivial convergent sequences. And then he realized of cardinality C. And then he realized that once you have that, you can, inside of that group, recursively construct your two counterexamples always. You don't need anything outside of ZFC for that. And actually, the existence of such a thing was proved, or that means countably compact group without convergent sequences was already proved using the continuum hypothesis a few years before that by Juhas and Heinal. So that solved Comfort's question consistently. And since then, there have been probably hundreds of papers giving partial solutions to this problem, but all of them consistent. So, and they all went the same way. They all constructed this countably compact group without non-trivial convergent sequences, assuming weaker and weaker assumptions. And the other thing that they had in common, they all use sort of inverse limit constructions. So they constructed the space as a subspace of 2 to the C or some power of a group of 2 to the C by just looking at it coordinate wise. So approximating points all at the same time. And what I want to tell you is, well, so we went looking for this sort of problem as a candidate. Is it consistently false, or can the construction be done in ZFC? Well, in this case, the construction can be done in ZFC. So in a joint work with Jan van Mil, Ariet Ramos Garcia, and Saharan Shela, we have managed to construct an example in ZFC. So we constructed a countably compact subgroup of 2 to the C without non-trivial convergent sequences, and therefore using the same method as Van Douwen, we also found two countably compact groups whose product is not countably compact in ZFC. And I want to tell you a little bit about the ideas which go behind it. So the first idea we looked at was looking at ultra powers. So if you have ultra filters, you can look at ultra powers of groups. I think everybody knows.
No.
No? All right. So what do? You look at powers of groups. So where are we?
Just in the statement just before,
2
to the C with the cardinality. So C is the cardinality of the continuum.
C is the cardinality of the continuum. Yes. So
in the slide before, that's just out of curiosity. So you said that there was examples again before.
Yes.
There are examples. How do you say? Consistent.
Yes.
So
all of those were examples of subgroups of 2 to the C too.
So that means that you are assuming some consistent extra.
Yeah. So here CH stands for continuum hypothesis. MA is something called Martin's axiom. MA countable is something called Martin's axiom for countable partial orders. So what these things are irrelevant to our talk at the moment. But yes, these are all constant axioms. You think well, exactly. So all right. So now about the ultra powers. So what is a countable product of a group? That's fine, right? We have no problem with that. But now we can quotient that out by a natural equivalence. And the equivalence is just looking whether two functions agree on a measure one set. So we measure one being the ultra filter. Okay. And from a logical point, the nice thing is, and that's why it's studied, is that the embedding of my group diagonally into the ultra power is what's called an elementary embedding, and I can actually so the new group, even though it's a lot larger than the one that I started with, has the same properties. So this is actually a construction which is used a lot in model theory, in set theory, in universal algebra. These ultra powers. Yes?
Could you just remove the pointer from G?
I could remove the pointer, yes.
Ah, thank you. Okay.
And this is very standard. What's less standard is that you can also look at ultra powers of topological spaces, and this is usually not done. So if you have a topological space with a fixed basis, you can give the ultra power, that means all sequences, countable sequences of element of X, with modded out by the measure one equivalence, a new topology. This is the topology which is naturally defined here. So a new open set on equivalence classes will be the set of those functions such that they fall with probability 1 inside of that open set. Okay, so I have an open set, and I have a sequence. Sequence is a function, and I say that the function will be in U star if with probability 1 or with measure 1, it falls into this open set.
The ultra power is still Hausdorff?
I wanted to avoid this question, usually not. So we have to do a little bit maybe of modding out, but let's ignore this. Sometimes it is. Sometimes it's not. But let's ignore this complication for a while, and let's pretend that it's always Hausdorff, but it's not. What is the question? The nice thing about for me when I want to think about these countably compact and p-compact things, that every sequence from the group down below from G now has a p limit, where p is the ultra filter I'm taking the ultra power with, and that's simply because the p limit is the class of the function itself. So the sequence is a function, and its class is an element in the ultra power, and no matter what topology I took, it will be a p limit. So if I now iterate this process, omega 1 many times, then I start with a group, say a topological group, and I make it grow omega 1 many times. So at the end, I will have a group, and I will have a topological space which is p-compact, because every sequence, because of cofinality, omega 1 has uncountable cofinality, so every sequence in that final group appeared in one of the previous group, and therefore is an element of the next one, and it's a p limit of the thing. So I have a p-compact group, but I have well, two problems. So if I now I want to turn this into a solution to this problem that I wanted. I wanted a countably compact topological group without non-trivial convergent sequences. I have two problems here. So is this thing that I constructed a topological group? It's a group and it has topology. That doesn't mean that it's a topological group. And the other question is, does it or does it not contain non-trivial convergent sequences? Well, I won't bore you with the details, but the plan can work. It actually works if we start with something called the Bohr topology on the Boolean group, and if our ultrafilter is selective. So it's a special property of ultrafilters. And in this case, the key lemma that you need to prove, which makes things work, is that if you take countably many functions from omega into the group, each representing different classes in the ultra power. So they are different modulo measure 1 everywhere. Then you can find infinitely many sets in the ultrafilter, such that if you push them through the sequences, then you have a disjoint sequence, and moreover, this disjoint sequence is linearly independent. And this is actually, if you don't know what a selective ultrafilter is, this is you can use this as a definition. So the problem is that selective ultrafilters don't always exist. Kunin showed that the existence of these things is the non-existence of these things is consistent. So essentially where I started, meaning I have constructed another consistent example to this thing before. But no, I've learned something. My construction is not an inverse limit construction. It's a direct limit construction of the group. Once I know the points, I already have them. They are not approximated. So I'm constructing my group from the inside, making it grow. And I know that I have a way of sort of manipulating the convergence using these ultrafilters.
Something bothering me.
Yes?
Why the linear independent condition?
What do you mean?
The last condition, they say that the sequence is linearly independent. What happens if it is not linearly independent?
Well, then I could have, linear independence is how I kill convergent sequences.
Okay.
Because I want to take a sequence and I want to show that I can find an open set, open neighborhood, which leaves infinitely many of the things outside. So how I do it, I can essentially prescribe the behavior which way I want because of linear independence, and then I create a homomorphism, which this has to do with how the Bohr topology works.
Yeah, I understand.
Okay, but this is a technical thing, but this is the lemma that makes the proof work.
Okay.
So now I will be very sketchy. So the proof.
Sorry. What is selective? What is selective ultrafilter? What is selective?
As I said, you can use the proposition as definition.
What definition? What a proposition? What is definition?
Well, if you don't want this as a definition, then the standard definition is whenever you partition omega into infinitely many pieces, either one of the pieces has measure 1, or you can select one point from each of the pieces such that that selector has measure 1, is in the ultrafilter. That's selective.
Thank you.
No problem. And what is sort of the idea behind the actual ZFC proof that we have? You still construct the topology inductively, as in the ultra power, just by sort of a more careful process. And rather than having one ultrafilter do the job, you will have many ultrafilters, which together do the job of one selective. And luckily, we can construct such a family of ultrafilters in ZFC. So this is as much as I want to say about the no convergent sequences, and we are going into the second part of the talk. But I'm already done, is that right? Half an hour, yeah, okay, good. So I'm halfway through.
You did this with the Bohr topology, but you can maybe do this with other topologies?
Actually, we've looked at that and it seems tight. So there are questions. So we can't make it work. We can make it work on, say, powers of Z3. So Bohr topology with the Bohr topology. But we can't even make it work for groups which are not of bounded torsion. So this is sort of very fine. There is something very fine about the argument. We don't know why, but it doesn't work even if you just take ultra powers of the integers.
Thank you.
So we don't know how to construct these ultrafilters. So the family of ultrafilters, which is easy to construct for the Boolean groups, we don't know how to do it for other groups. And so the advantage of the ultra power method was that I constructed not only a countably compact group, but a p-compact one. And that we don't know either, whether that can be done in ZFC. So these are some of the interesting questions. So the one about non-torsion would actually solve an even older question of Wallace about topological semigroups. So there is still work to be done in this area, but let's move on. So now the second half of my talk is about topological groups which have many convergent sequences. So they have so many that actually their topology, the closure operators are determined by convergent sequences. So other than metric, the second nicest class of spaces is the class of Fraissé spaces. That means if I want to know the closure of a set, I just add to the set the limits of all convergent sequences. And I arrived at closure. So spaces with that property are called Fraissé. Sequential spaces are similar, so I can also get to the closure by taking limits of convergent sequences, but I have to iterate the process. That means I start with a set, I add convergent sequences, it gets bigger, but it doesn't give me all closures, so I take convergent sequences, something. This new thing, it gets bigger, it gets bigger, and eventually the closure set space that I so and the number of steps that I need to take, or number of iterations I need to take of taking limits of convergent sequences is called the sequential order of the space. So this is an ordinal parameter that it's given to the space, and it's a countable ordinal. It's an ordinal below omega 1. Okay. And again, to show you how little we know, this is probably the second, my second favorite problem about topology passed after the Yefimov problem that I mentioned a little while ago, and it's Arkhangelski's problem, whether there are compact sequential spaces of sequential order bigger than 2. So from something called a maximal almost disjoint family, we can construct a compact sequential space of sequential order 2, and using again CH or something, we can construct compact sequential spaces of sequential order, any ordinal below or equal omega 1. But in ZFC, we can get to 2 and not even to 3. So again, I think very interesting problem in set-theoretic topology. And now for topological groups, again, the thing is that things should improve if we add algebra. So there are many Fraissé spaces which are non-metrizable, even compact ones. But Malikhin realized that even though he can get consistent examples of separable or even countable Fraissé groups, which are not metrizable, he didn't know how to construct one in ZFC. And a similar problem was roughly at the same time asked by Peter Nykosh about sequential groups. So he realized that there are sequential groups of sequential order 1, meaning Fraissé, because there are metrizable ones. And then there are very complicated ones of sequential order omega 1. But what about all these ordinals between 1 and omega 1? What about 2, 3, omega, all these ordinals? Well, there were consistent examples, but none in ZFC. And again, Fraissé and sequential groups, in general, the property is not productive, but how exactly that they behave, well, there are, again, many papers about this, but they all deal with consistent results. So these three questions drove research about sequential and Fraissé groups for many years. And as I said, for the Malikhin's problem, there were many consistent examples. You don't have to worry about what these things mean again. It all just means these are some principles which say that the existence of a non-metrizable Fraissé group is consistent. But finally, in 2014, with Ariet Ramos Garcia, we have constructed an ad hoc forcing model where we showed that this time there is no ZFC answer. Unlike in the first example that I gave you, here, this question is independent of the axioms of set theory. And a similar thing happened with the sequential question of Peter Nykosh, where much of the research was done by Alex Shibakov, where he first constructed under several assumptions, weakening assumptions, counterexamples or examples of groups of intermediate sequential order. And finally, after he saw our result with Ariet, he has managed to come up with, again, a forcing model where he proved that the question is independent. And finally, we got together and we said, well, these models are different. They are nice, but we should find a way of proving these theorems that we can actually articulate. We can tell people what they are. And we have come up with this invariant ideal axiom, which in its diluted form says that if you take a countable sequential topological group, in its non-diluted version, it has a much wider class of groups than sequential. If you take an ideal, so ideal is measure zero sets. So if ultrafilter was measure one sets, for the same measure, just take the measure zero sets, okay? So it's the dual notion to a filter. And invariance just means that it's invariant under translations in the group and under inverses. Okay, so if you have something in the ideal, then all of its translates are also in the ideal, and if you have something in the ideal, its inverse is also in the ideal. So that's what invariant ideal means. So if you have a countable sequential group and an invariant ideal on its power set, then one of two things happens. So either there are countably many sets in the ideal which know convergent sequences. Okay. By knowing, meaning every convergent sequence intersects infinitely one of the sets in the ideal. Or there are countably many things which are of positive measure, meaning they are not in the ideal, which sort of behave like a pi basis for the topology, meaning every open set in the group contains one of the countably many modulo a measure zero error. Okay. So what we have done is we have proved that this invariant ideal axiom is consistent, and we have deduced the two theorems from the axiom. So Malichin's problem, so every countable separable, or every countable Fraissé group is metrizable, equivalently every separable Fraissé group is metrizable. I had a proof prepared, but I think I'm going to skip it just because I want to maybe tell you something more interesting at the end. And also, there are no sequential groups of intermediate sequential order, but we actually proved something much stronger. We gave a complete classification of countable sequential groups from this invariant ideal axiom. But for that, I need to give you a few more definitions. So bear with me. A topological space is K omega if there is a countable family of compact sets which knows the topology, meaning a set in the space is open if and only if its intersection is open with every one of these countably many compact sets. Okay. So to know the topology, all you need to know is these countably many compact sets. And now if you look at K omega groups, then countable K omega groups, they have F sigma topologies, because if you think about countable compact spaces is just copies of ordinals. So I have countably many closed definable sets. So they're coded by a real very nice Borel set. And all I'm saying is that somebody is open if and only if for every the condition of openness is simply an F sigma delta condition. So that means these K omega groups are very much definable objects. We can tell what they look like, and you can't kill them. They are there forever. And what we have proved, well, I'm not going to tell you quite yet, but I want to mention this theorem of Zelenyuk, that there is a very simple ordinal invariant. You just take, so if you are K omega, that means you're given countably many compact sets. Each one of these compact sets is homeomorphic to an ordinal. Just take the supremum of these ordinals that you are homeomorphic to, and that defines an ordinal characteristic of the group. And the theorem says if the two groups have the same ordinal characteristics, then they are isomorphic. Well, the topologies are homeomorphic. The groups are not necessarily isomorphic, but we know the topology. And what did we prove? Oh, sorry. Well, here is just, you can actually find nicely definable representatives of these classes. So there are really, so if you think of it as an equivalence relation, it's an equivalence relation with omega 1 many classes, okay? So what we proved from the axiom is that every countable sequential group is K omega or metrizable. So in particular, it solves both of these problems that we wanted to look at and more. It gives a complete classification of these objects. People were constructing many pathological examples using CH and MA and all kinds of weird things, but they all disappear in this model. There are only the things that have to exist. All the topologies are Borel in particular on these things. And it also tells you about products. So you have sort of two classes of sequential groups. You have those which are metrizable and those which are not. And each class separately is productive, but when you go across, they're not. So it also determines uniquely the products of these things. So every sequential group, countable or uncountable, contains a copy of a space which is called sequential fan. Just take countably many sequences and glue them by their last point. So this is a special sequential space that would exist in every sequential group, which is not metrizable. And now if you have a metrizable group, say the rationals, then you will have something which you would call a convergence sequence of discrete sets. So we have an infinite discrete sets, and you have another infinite discrete set, and they're getting smaller and smaller and smaller, so that the limit contains all but finitely many of those. Now, if you take the product of these two very nice spaces, the sequential fan and the product of discrete spaces, then their product is not sequential. In language of Borel ideals, it essentially says that the ideal generated by thin cross empty and empty cross thin, which is thin cross thin, is tall. It doesn't have pseudo things in the orthogonal, so it doesn't have convergent sequences at all. So this is a very nice and definable example, which I actually had on my slides originally, but I decided not to put it there because of time.
Okay.
And this is one that you can't get rid of. And it's the only one. So every non-product theorem about that you can prove in ZFC just boils down to this. All right, so let's skip the questions. You can take a look at this invariant ideal paper if you're interested in this, and I'll just give you in the last what I have 10 or so minutes a third topic that I wanted to talk about, and it's about Polish groups. So probably looking at, I have seen some of the people here before, and they're probably much more interested in Polish groups than what I've talked about so far. So what are Polish groups? Polish groups are nice groups. They are metrizable and separable and complete. So they are completely metrizable Polish groups. And for those, you can have, of course, a very nice theory, and they have been studied also in connection with, say, methods from geometric group theory. And one of the classes that is studied a lot is the class of non-Archimedean groups, that is groups which are classified by countable structures or simply closed subgroups of the group of permutations of the integers. And the nice thing about that is that these groups are all isomorphic and topologically isomorphic, as topological groups to automorphism groups of ultra-homogeneous structures. And these are, again, nicely approximated by finite objects using something which is called Fraissé theory. So I guess many people here have learned about Fraissé theory, but for those who haven't, I will just briefly recall the main theme. So what it means for a structure to be ultra-homogeneous, and this is, again, sort of an application of, say, model theory to topological algebra. So if I have a structure M, what does it mean for it to be ultra-homogeneous? It means that if I take two finitely generated substructures, A and B, and an isomorphism phi between them, then I can find a global isomorphism which extends the partial one. Okay, so this is what ultra-homogeneous means. And if I have an ultra-homogeneous structure, then I can look at all the finitely generated substructures, and just by looking at the class of finitely generated substructures, I can tell whether it's ultra-homogeneous or not by looking at these two properties, the joint embedding property, which just simply says if I have two of these finitely generated structures, there is a third one where I can embed them, and the amalgamation property, which is slightly more complicated. It just says that if I have three structures, A, B, and C, and an embedding of A into B and C, then I can find, so for every this, there are these two things, so psi 0 and psi 1. There are embeddings B of C into a D, such that the diagram commutes. So this is an amalgamation property, okay? And on the other hand, if I have a hereditary class of finitely generated structures which have these two properties, I can recover the countable ultra-homogeneous structure by constructing something called the Fraissé class, and that it will be an ultra-homogeneous structure. So, but as I said, what I'm really interested in are the homeomorphisms groups of this, which are subgroups of S infinity, closed subgroups of S infinity. So in particular, one of the questions that has been looked at recently is the automatic continuity of structures of this form. Martin has been looking at automatic continuity of, I think, isometry groups, right, mostly. But this is a very interesting topic. And what I have been looking at with some friends is looking at homeomorphism, groups of homeomorphisms of nice spaces, right? So here on this slide, I just want to say something about automatic continuity very briefly. So one of the first things I tell my students when they enter my set theory class, I ask them a question. So are the reals and the square of the reals, are they the same group? Are they isomorphic? Let's say, well, they're both vector spaces over the field of rationals of the same dimension, of dimension C. So by just a basic theorem of linear algebra, they are isomorphic as vector spaces, therefore they are also isomorphic as groups. So I ask the second question, where is the isomorphism? And there isn't any, right? There isn't any because one reason for that is this Banach-Pettis theorem. If I could write out an isomorphism between them, between the two Polish groups, then such automorphism would be a homeomorphism, isomorphism. But the reals and the square are not homeomorphic because, well, one has dimension 1, the other one has dimension 2, or more simply, if I take a point from the reals, I make it disconnected, but if I take a point from the plane, it remains connected. So they don't have the same topological properties, they cannot be homeomorphic. All right. So what I really proved is that neither reals nor the square have the automatic continuity property, meaning there are non-continuous homomorphisms into Polish groups, but there are many, surprisingly many Polish groups for which the automatic continuity property holds. Some of them are, for instance, the homeomorphism groups of the reals or of contraset. In fact, the two papers by Christian Rosendahl and Katie Mann, where they prove successively that all compact surfaces, the homeomorphism groups of compact surfaces, have automatic continuity, and extended by Katie to all compact manifolds of arbitrary dimension. These are really non-trivial results. So what we were looking at were groups of homeomorphisms of surfaces which are not necessarily compact. Okay, so if you have a surface of infinite type, that essentially translates immediately into that the Polish group of, which is the mapping class group, the one in the middle is not countable, but it's a Polish group. Then we can look at automatic continuity of these three naturally associated groups. So this one is just the group of homeomorphisms of the surface with the compact open topology. That's a Polish group. This one is the factor group of this one by homotopy. And this one is very interesting to geometers, these mapping class groups. And then you can think of the space of ends. So if your surface is, for instance, take a sphere and take away a contraset from the sphere, then the contraset becomes the space of ends of this surface. All right. So you have these natural surjections between these three Polish groups, and the question which ones of them have the automatic continuity property is pretty much an open project, interesting project. So there are some partial results. Katie has shown that there is a mapping class groups for which you do have automatic continuity. In particular, the one that I just mentioned, take away a counter set from a sphere. And she also noticed that there are surfaces for which you do not have automatic continuity, and George Douwen and company are now studying the problem of generality. Nice. So the thing is, these guys and these two, they can be seen as automorphism groups of Fraissé structures. For the mapping class groups, you look at something which is called a curve complex of a surface, which is a countable graph. And just massaging it a little bit, you can turn it into an ultra-homogeneous structure and apply the Fraissé group technology. And the homeomorphism group of a compact zero-dimensional space is by Stone duality. Same thing as the automorphism group of a countable Boolean algebra. And again, you can apply the Fraissé technology to the automorphism of groups of countable Boolean algebras. So a nice way of checking whether something has automatic continuity is by checking a property which is called ample generics. I don't have time to explain what it is, but I can say it. It just means that if I take the diagonal conjugacy action of the group on its finite powers, then I have a comeagre orbit for every such. But we have shown that this actually doesn't get you anywhere, because for these mapping class groups, you never have ample generics. And then we decided to look at the simplest cases of these end spaces, which are just countable spaces. They are countable compact metric spaces that are homeomorphic to ordinals. So there we show that in a so far unpublished and not completely written work yet, we show that you have ample generics if and only if the ordinal is a successor of an indecomposable ordinal, and you always have automatic continuity. And I think this is all I wanted to say. So thank you. And I'm pretty much right on time.
Okay, thank you. Merci. Are there questions? Il y a des questions?
Martin?
What is the example of a surface for which the mapping?
Yep. So imagine that what I'm drawing on is the globe. Okay. So I have a counter set, and in the counter set I pick a convergent sequence, which will converge to this point over here. Okay. And I will think of it as a convergent sequence of pairs. Okay. And now I will glue to this guy an omega convergent sequence to each one of those guys. And to these guys, I will draw omega square convergent sequence. And to the nth guys, I will have to omega to the n convergent sequences. And it all is sort of a nice so that it converges to this one point, so that it's a compact space. Okay. So now notice that neither the mapping class group of the surface, which is the complement of what I have, but nor the homeomorphism group of just the n space have automatic continuity, because you have the surjection of, say, this is E onto Z2 to omega, which doesn't have automatic continuity, because what does every homeomorphism do? It either keeps the pair alone or it flips them. And you can do any combination of those things. So this gives you a group homomorphism onto this guy, and that gives automatic continuity. Is that okay? The one that does is just the counter set itself. And my suspicion is, so you can have counter set and sort of finite garbage. finitely many punctures of finite genus. And I would suspect that essentially that's all, that all the other surfaces will give you.
So, is it simpler, the book for the sphere minus the composite?
I should know that, but I don't, but I'm sure it's known.
Is it known for like finite genus surface, whether it's like the matter class group is like have the automatic
For which, sorry?
like finite genus surfaces?
Finite genus surfaces. Well, it depends. This one has finite genus because it has no genus. So it doesn't, right? But if you just add, if you just look at the counter set and the finite genus, so if you have the complement of the counter set in a sphere plus some finite genus, then this does have automatic continuity. So sometimes, the answer is sometimes.
You have other questions, comments? Okay, thank you very much. I think